Thank you very much. Thank you for giving me the opportunity to give this talk. I'm happy and honored to be here. Michel was one of the very first mathematicians to show interest in my work right after my PhD, and it was very nice to receive, well, to see that some people could be interested in these kind of things, even though they were not the closest topic to their many interests. So what I'm going to explain is in fact related to what I did in my thesis, but a bit different. So this is joint work with Roman Bezrukavnikov, and so in fact this also has some connection with the talk that we just saw, in that it's well, it's about well, the main objects of interest are representations of Lie algebras in characteristic P, but well, at least what we do is unrelated to any p-adic story. So I should first explain what I mean by Harish-Chandra Bimodules and why I am interested in such things. So I would work over K, an algebraically closed field of characteristic L, which I take to be positive, and I want to take G, a connected reductive algebraic group over K, and I want to fix, as usual, a maximal torus and a Borel subgroup. And I will need a notation for the Weil group, W, so normalizer of T constituted by T. This is a finite group. And I need notation for the Lie algebras of my group. So Gothic G will be the Lie algebra of G, and the same for B and for T. So the main object of study are Harish-Chandra bimodules, and in this setting, Harish-Chandra bimodule, this is a bimodule, so attached to my group G, is a bimodule for the enveloping algebra of my Lie algebra. So this is a UG bimodule M, which is endowed with an action of G. Of my group G, such that two conditions are satisfied. The first is that, well, in fact, I have a G-equivariant UG bimodule, so this means that the map from UG tensor M tensor UG to M, given by the actions on the left and on the right, is G-equivariant, equivalent for the group, with respect to the action on the left-hand side, given by the adjoint action on the Lie algebra and on the enveloping algebra, and then the diagonal action on this tensor product. And the second condition is that the differential of the action of G of the group. So I have an action, an algebraic action. Yes, when I said an action of G, I mean an algebraic action of the group. So I get, if I differentiate this action, I get an action of the Lie algebra of G, and this action of the Lie algebra should be related to the action of UG in the most natural way. So the differential of the action of the group G is given by the following action of the Lie algebra on M. it's the diagonal action, so it sends an element x. So here x is in the Lie algebra and m is in the module M, and so x acts on M by sending it to xm minus mx. So in other words, Harish-Chandra bimodule, it's a bimodule such that this diagonal action can be lifted to an action of the group. And since we work in characteristic P, this upgrade of the action of the Lie algebra it's not a condition, it's really a datum, it's not uniquely determined. You need to specify this lift of the action of the Lie algebra.
It's an action of the algebraic group, right?
Yes.
Not of the K point of G, you mean?
No, I really mean the...
Everything's algebraic.
Yes, when I say an action, it's so an algebraic action. An action in the sense of algebraic groups. And so there are some natural examples of such things, such bimodules that we can get if we start with a representation of the group. And there are, so if I start, so rep G will be my notation for, so this is the category of finite dimensional algebraic representations of G. Well, so the finite dimensionality at this point, it's not important, but later I will need some finiteness assumptions, so it's just assumed in the definition. Then if I take V representation of the group, I can take M to be V tensor UG with the diagonal action of the group G. The left action of UG, which is the diagonal action. So namely, UG acts on UG by in the natural way on the left. And I also have an action on V coming from the differential of the action of the group. And so I take the diagonal action, and this gives me the left action. And the right action is only on the right factor. So if you think about, well, if you think about it for a minute, you should be able to convince you that this satisfies the requirement. And another, so that's one important example of Harish-Chandra bimodule. And another, so this was supposed to be an S, sorry. And another example, which is even simpler, is to take a V with the natural G action, the left action of UG given by the differential of the action of the group. And the right action, which is trivial. Once again, it's easy to see that my requirements are satisfied. And the reason why I want to consider these kind of things, so the first reason is that these things, they form a monoidal category. So the category of Harish-Chandra bimodules give me a monoidal category. Well, if I work at the abelian level, I want to consider just tensor product of bimodules, and it will give me some monoidal abelian category. And if I want to work at maybe with derived category, I want to take the derived tensor product of bimodules, and it will give me a monoidal triangulated category. And it acts on G-equivariant representations of the enveloping algebra. And well, in here, I have the special case of G-equivariant UG modules where the action of the Lie algebra is just the differential of the group, and this subcategory is just equivalent to representations of G. And yes, well, so in my notation for RepG at this finite dimensional, well, so this contains all algebraic G representations, and the action of Harish-Chandra Bimodules on this category of modules will stabilize G representations. And again, I see a G representation as a G-equivariant UG module where the action of the Lie algebra is just the differential of the group. And so this means that these objects they produce some symmetries of this category.
So the action is by tensor product, right? Or is it?
Yes, it's a bimodule, and this is a category of modules, so I just let bimodules act on module by tensor product. So I will come back to this this point of view in a minute. But before that, I want to explain some variation on this definition, which is in fact more interesting. But so for that, I need to say a few things more about these bimodules. So the first thing has to do with the action of the center. So I work over a field of positive characteristic, and so in the enveloping algebra, I have a large central subalgebra, which is the subalgebra generated by elements of the form x to the L minus x to the bracket L. So for x in the Lie algebra. So this is a subalgebra in the enveloping algebra. So here, x to the L means the Lth power of x in the enveloping algebra, and x to the bracket L means the restricted Lth power. So this is an operation that we have on any Lie algebra of an algebraic group over a field of characteristic L. And so this x to the bracket L is another element in the Lie algebra, and it's important but standard observation that elements of the form x to the L minus x to the bracket L are central in the enveloping algebra. And so the subalgebra generated by such elements, so this is a central subalgebra, which identifies naturally with functions on the dual, well, the Frobenius twist of the dual of G. So yeah, I have this this central subalgebra, and whenever I have a representation of, well, a module of a UG which comes from a representation of G, this central subalgebra has to act through the trivial character, so the character corresponding to the element 0 in the dual of the Lie algebra. And because of that, when I consider Harish-Chandra bimodule, the action of UG tensor UG up on any Harish-Chandra bimodule factors through an action of the tensor product over the Frobenius center. So again, this is due to my second condition. So this diagonal action, it comes from an action of the group. So the Frobenius center. So this ZFR is called the Frobenius center. The Frobenius center has to act via the trivial character, and this translates into this condition that the two copies of the Frobenius character act in the same way. And this tensor product I will denote it by U, just for simplicity. And so that's what happens for one part of the center, but there is another part of the center, so there is another central subalgebra, which is which resembles the center that we have in the case of characteristic zero coefficients. This is just given by G invariance in the big algebra, and this is called the Harish-Chandra center. And geometrically, at least under some very mild assumptions, this identifies with the quotient of the dual of the Lie algebra of the torus by the Weil group, and this W dot is for the dot action, which is very similar to the dot action that appeared in the previous talk. W dot psi is W of psi plus rho bar minus rho bar. So if we are not in characteristic 2, this is just, so we have this rho, which is the half sum of the positive roots, which always makes sense as an element in the dual of the Lie algebra of the torus. And well, in characteristic 2, you can do something similar. So we have this this twisted action, so this Harish-Chandra center, this is another central subalgebra in UG. And so as for U, so U contains a central subalgebra, which is I will denote by Z, which is the tensor product of ZHC with itself over the intersection with the Frobenius center. So I just take my Harish-Chandra center on both sides, and because I took the tensor product over the Frobenius center, I get something. Well, I get the tensor product over the intersection, and geometrically this corresponds to functions on T star mod W dot cross T star mod W dot over T star 1 mod W. So this corresponds to this intersection. And the map from, well, here the map from T star mod W dot to T star 1 mod W is given by the Artin-Schreier map. So well, this, what it is precisely is not so important, but well, this is something very explicit. And so we will be interested in some modules over this algebra U, which have some properties with respect to this center. More precisely, now I want to take two characters of the torus, which I can see. Well, yeah, I can take the differential to get elements in the dual of the Lie algebra of the torus, and I want to introduce some notations. Z lambda hat mu hat will be the completion of Z with respect to the ideal, well, the maximal ideal corresponding to the image. Well, so a maximal ideal of Z is determined by an f point of this scheme, and I will take the point given by the image of the differential of lambda in the first factor and the image of differential of mu in the second factor. This gives me an f point in here. And
sorry, for the tensor product of Z, you take the Harish-Chandra center on both sides, or one Frobenius and one Harish-Chandra?
No, I take Harish-Chandra. So I have two copies of UG, and I take the Harish-Chandra center on both sides, and it is tensored over the intersection because in U I have taken the. Yeah. So I want to specify the Harish-Chandra character on both sides. And more specifically, I want to work with some generalized character, and so that's why work with completions rather than quotients. And so this is z lambda hat mu hat. And then I have the u lambda hat mu hat, which is the tensor product of u with this completion of the center. So here u is not a finite module over this central subalgebra. So well, this tensor product with the completion is not the completion of the algebra, but this is really what appears in what I'm going to explain next. And finally, I want a version of Harish-Chandra Bimodules for this algebra here. So I will denote by HC lambda hat mu hat, the abelian category of finitely generated Harish-Chandra u lambda hat mu hat modules. So by this, well, I will not write the details, but I can explain this. So this algebra u lambda hat mu hat, it has an algebraic action of G. Well, this is one of the reasons why I don't want to work with the completion of u with respect to some ideal, but really with this tensor product, because on the completion the action would not be algebraic. But in here on this tensor product, I have an algebraic action of G coming from the action on u, and I want to consider what I call Harish-Chandra bimodules for this. Harish-Chandra modules for this algebra means a module together with algebraic action of the group, which satisfies exactly the same. Well, the obvious counterpart of one. So now the action of the algebra, the map giving the action of the algebra on M is equivalent for the action of the group. And again, I have this action of the algebra given by this rule, and I want this to be the differential of the action of the group.
Sorry, so you add an extraction of the u lambda mu, or you want just to replace ug by u lambda mu in the differential?
I want to, in this definition, I had a bimodule for ug, so I had a module for ug tensor ug opposite, and I want to replace ug tensor ug opposite by this. So yes, so this is essentially the same as this, but the action of the center is extended to the completion.
No, but how, if this is kind of a strange tensor product where they're not without finiteness conditions, so if you work with finitely generated, usually to have an abelian category, you need something like a Noetherian or coherent ring or something, some nice ring.
So this ring is Noetherian.
Okay.
So it's finitely generated as a ring over this, which is Noetherian. So it's still Noetherian. So finitely generated is not.
Filter with a good filter. Okay.
Okay. And yes. So now I can get back to this this remark that I had that these
Could you just clarify how ZFR goes into Z in this formula of tensor product?
So it's just Z. It's a subalgebra in U, which is UG tensor UG over the Frobenius center. Well, so what is obvious is that there is a map from Z to here, given by just you send ZHC to this copy, this to this other copy, and so this gives a map.
And ZFR goes to.
Well, so in here, I have taken the tensor product over the intersection.
The intersection goes into ZHC, but I don't see how it is. ZFR goes to Z. Yes.
No, but the map is from here to here. So this is a subalgebra of this. So the tensor product makes sense. And this maps to here just because this maps to here, this maps to here, and this maps to here because this is also a subalgebra in here.
But ZFR is not a subalgebra of Z, no?
Z is just.
No, but ZFR. So this is the definition of Z. Well.
No, but it takes the intersection. So.
It is not the center.
No.
Well, no. Yes. So this is not the.
It is not the center.
No, this is this is a commutative algebra that maps to U. That's. But no, no, I'm not claiming that this is the full center. No, this is smaller than.
I thought you meant the full center.
No.
The description in terms of the twirl of the algebra of the toes, do they require that the characteristic is not very small in some?
Yes. When I so in this identification, yes, there are some mild assumptions. I'm not making them explicit because I didn't prepare that, but yes, there are some mild assumptions to make sure that that we have a Harish-Chandra isomorphism. So these things with completions appear when we consider the following situation. So now I go back to my category of UG, so of G-equivariant UG modules, but now I want to restrict to finitely generated modules, and I want to add some lambda. This is the category of finitely generated G-equivariant UG modules. Such that the Harish-Chandra center acts with generalized character lambda. So to act with generalized character lambda, this by this I mean that the kernel of the character acts nilpotently on such modules, and this. So I explained that G-equivariant UG modules contain, in particular, G modules, and in here the corresponding subcategory will be, it is something very important in representations of reductive groups of fields of positive characteristic. This is the full subcategory of so finite dimensional representations of G consisting of modules, all of whose composition factors are of the form L of W dot lambda plus, so the composition factors, so the simple objects in the category rep G, they are classified by the highest weight, and I want the corresponding highest weight Horowitz composition factor have highest weight in W dot lambda plus L times a character. So, and again, this dot is, it's the dot action of the Val group now on the character lattice, but which is given by a similar formula as before. And weights of this form. So yes, this is closely related with the orbit of the affine Val group acting on lambda. And so these kind of subcategories rep lambda, they are called blocks in representation theory of reductive groups over in positive characteristic. And yes, there are things that we like to study a lot. And these kind of blocks, they are related by the so-called translation functors. And in fact, translation functors are special cases of actions of Harish-Chandra bimodules in this sense, in the following way. Any m in my category HC lambda hat mu hat determines a functor from my category of modules for the enveloping algebra corresponding to mu to modules, or the similar category corresponding to lambda. Just once again by letting a bimodule act on modules, and it will respect representations of the group. So in here I have rep mu of G, and in here I have rep lambda of G. So this gives me a functor in here, and using objects. So I explained how to attach some Harish-Chandra bimodules to representations of the group at the beginning of the talk. And in particular, I had these objects of the form V tensor UG. And these V tensor UG, now I want to tensor them over my central algebra Z with Z lambda hat mu hat. And this gives me a module for my new algebra, U lambda hat mu hat. And if I consider the functors associated to these modules, I get the translation functors. One obtains the translation functors. Well, so these translation functors, so they were first constructed by Janssen in the setting of category O of complex semi-simple algebras, and then Janssen himself also considered them in the representation theory of reductive groups in positive characteristic, and they are, well, very important functors in this theory. And so there are some examples of symmetries of the category of representations of the group, and now I want to interpret these symmetries as just actions of some particular cases of Harish-Chandra bimodules.
So the translation factor is by tensoring the representation by the bimodule. So you have to take a component, or you take the full tensor product?
No. Well, so these translation factors, exactly, they are given by tensoring with some G module and then taking some components. But taking this component is taking care. Well, it's realized here by this tensor product with the completion. That's what the completion. Well, in this setting, that's what the completion does. It just specifies one direct factor of the tensor product. Yes, but so what is useful about this point of view is that now instead of just composing some functors, well, if you want to consider some compositions of these of such translation functors, instead of having to compose functors, which is something very abstract, you just have to take tensor products of modules, which is something that you can more easily work with. So this is one reason why Roman Bezrukavnikov and I got interested in these Harish-Chandra bimodules, and the way we were able to say something about these objects was using geometry. And so I want to explain some geometric realizations of Harish-Chandra bimodules. So the first, well, in fact, there will be two geometric realizations. The first one is is really what I had in mind when I said localization theory, and this is the coherent picture. This will be a geometric way of studying Harish-Chandra bimodules in terms of coherent sheaves. And so in here we assume that so my characteristic L is larger than the Coxeter number. So H is the same H as in the previous talk, so it's the Coxeter number. And I will restrict to the case when the central character is 0. So the trivial central character, so assuming that L is larger than H, this is a regular character, and in some sense this is the only central character that you really have to understand. I mean, if you understand this character, this central character, you can just spread the information to other characters in some way. So the geometric object that appears in this coherent picture is the Grothendieck resolution. So it's denoted G tilde, and it consists of pairs psi GB. So psi is an element in the dual of the Lie algebra, and GB is an element in the flag variety G mod B. And I require that, okay, I should have introduced more notation. So I will denote by U the unipotent radical of my Borel subgroup B, and by U it's Lie algebra. So it's the same. In the end, it's the same U as before, and I require that Xi vanishes on the G translate of U. Well, so G is only determined up to an element of the Borel subgroup, but it doesn't change this subalgebra. So this is so G tilde is it's a vector bundle over the flag variety. In particular, this is a smooth scheme. And it has natural maps. So G tilde, so it maps to G mod, well, it's again a vector bundle over G mod B, but that's not so important for me. So it maps to G star just by sending you a pair to Xi. And there is another map to T star. And this map sends a pair X GB to Xi GB to G inverse dot Xi. So G inverse dot Xi is an element of the dual of G, which is determined only up to conjugation by an element of B. But I want to restrict it to the Lie algebra of B. And so I will get a linear form on B, but which is 0 on U by assumption. And B mod U naturally identifies with T, so this identifies with T star in and so this is the map to T star. And now I want to consider the Steinberg variety. By definition, this Steinberg variety, well, so there are several things that we can call the Steinberg variety, but for me, this will be the fiber product of G tilde with itself over G star. And so now this is just some scheme, which is not smooth anymore. And it naturally maps to, so I have a map from G tilde to G star, from the right G tilde to T star, and when I take the fiber, because I took the fiber product, it factors through an action to this fiber product of T star and itself over this quotient. And just so in the previous story, I had this thing about tensoring with some completions of the center, and in geometry, I have a similar phenomenon that I need to consider completion of this. So I will denote by T star cross T star over T star mod W 0 hat 0 hat. The spectrum, so now I want to take the spectrum of the completion of functions on this fiber product. So the completion with respect to the maximal ideal corresponding, so maximal ideal corresponding to the point 0, 0 in T star cross T star over T star mod W. So I take the completion of the ring and then of this ring, and then I take the spectrum. So this is just an affine scheme. And I will denote by ST hat the fiber product of ST with this affine scheme over T star cross T star over T star mod W. So once again, I get just a Noetherian scheme with an algebraic action of the group G. And so now I can state the theorem giving the first geometric realization of Harish-Chandra Bimodules. So it states that there exists an equivalence of categories of triangulated categories between the bounded derived category of these Harish-Chandra bimodules associated with 0 and 0 to the derived category of coherent sheaves on the Frobenius twist of this Steinberg hat, which are equivariant with respect to the Frobenius twist of G. And yeah, so this, geometrically, this Frobenius twist here is related to the appearance of the Frobenius twist in my description of the Frobenius center, just on the board above, because yes, geometrically, this Frobenius center corresponds to this this G star here. Well, in this story, we will see the Frobenius twist of this.
This so the Steinberg completion is an algebraic variety, right?
This is not a finite type over F, but this is a finite type over this completion.
And this completion is what?
It's some Noetherian ring.
It's a Noetherian.
Yes, it's the completion of something Noetherian, so it's still Noetherian. Yeah, so I want to make a number of remarks on this result. So the first one is that this is an equivalence of monoidal categories for a certain monoidal categories, but I didn't explain properly the monoidal structure on the right-hand side. And here for a convolution product, there is a natural convolution product on the right-hand side. And with respect to this convolution product, we get an equivalence of monoidal categories. Second remark is that the proof is, the proof builds on the localization theory of Bezrukavnikov, so the localization theory of Bezrukavnikov-Mirkovic-Rumynin. So this localization theory that I refer to is an analog of the localization theory of Beilinson-Bernstein, which was concerned with describing representations of Lie algebras over fields of characteristic 0. But this is a counterpart of this theory for representations of Lie algebra over fields of positive characteristic, which was developed by Bezrukavnikov-Mirkovic-Rumynin in the early 2000s. And so roughly, it's so in the classical theory, in the original theory of these authors, one just studied modules over UG, and the UG modules in there. So I will not be precise. I mean, there are of course precise statements, but I want to be just to give an idea and not go into the details. The UG modules, in their theory, they are related to D modules on the flag variety G mod B, and the relation is as in Beilinson-Bernstein theory. So in this direction, it's given by global sections, and but then in the usual theory of Beilinson-Bernstein, one goes from D modules to perverse sheaves. And so this part of the theory is different. Here the D modules, they go to coherent sheaves on, let me write the Frobenius twist of the Grotnik resolution, and in here this Grotnik resolution, it appears as some kind of central subalgebra of the algebra of differential operators. And when I say D modules, I mean crystalline D modules. So the the most basic things the most basic the most basic kinds of D modules that you can think of, just modules over the enveloping algebra of the tangent sheaf.
So your model here, right?
Everything, yes. So in the classical theory of Benison and Bernstein, you are over the complex number, but in this story, you are in my setting of characteristic L. So this side, this part of the construction is similar to the one of Benison-Bernstein, except that you really have to work at the level of Dirac categories and not abelian categories. And the second step is different. It builds on, well, it uses some specific features of the algebra of differential operators on smooth scheme in characteristic L, which is an Azumaya algebra, and this Azumaya algebra can be, well, it splits on certain subschemes, and that's how you pass from D modules to coherent sheaves.
Just an example.
What do you mean by an example?
You don't see Pogus-Vologodsky in the second
This
one?
functor from the second functor. Yes.
Oh, well, so it's just that, as I said...
There may be a trivial example, and then not so trivial. So take O, for example, what do you get?
I'm sorry?
You could take O, for example.
If you take, I didn't want to go into the details. Here, to pass from here to here, you really have to restrict to some subschemes. This Azumaya algebra. So, well, the passage from here to here is just essentially the fact that, so D is an Azumaya algebra over its center, and when you put some conditions on well, if you restrict the center to certain things, this Azumaya algebra splits. So your algebra will become anamorphisms of some vector bundle, and then the relation with coherent sheaf is just that.
There's not really a functor.
No, I'm not. So this is just the rough picture. I mean, if you want to get a functor, you have to restrict to some subcategories.
There is some relation. But
Yes. No, I'm not claiming that the two categories are equivalent. I'm just saying that there is a way to build some functors between some subcategories, but one has to go into the details. So what we do to prove this theorem is, well, it's just repeating this story, but now with modules over, with bimodules. So this corresponds to D modules on two copies of the flag varieties, and coherent sheaves on this product of two copies of this. So there is a relation with coherent sheaves on product of two copies of the Grothendieck resolution. And so the fact that Harish-Chandra Bimodules factor through modules over the tensor product over the Frobenius center means that on this side we get coherent sheaves on the fiber product that appeared here, and then there is something specific about bimodule is that one can get, well, the situation compared, well, corresponding to this. This row here is better, and for this category of bimodules that we get, we can construct explicitly some splitting bundles and some splitting bundle and get the relation that we have here. And so that's what I wanted to say about the proof. Now. Third remark is that we had Roman Bezrukavnikov and I had an earlier result of the same kind, but where we only looked at what happened over the regular part. So in a sense, again, I'm not going to be very precise, over the regular part of G star, and so essentially this means that, well, at the level of geometry, this means that we just restrict to the open, well, the preimage of the open part in G star consisting of regular elements, and over the regular part we get an equivalence at the abelian level. instead of, we don't have to go to Dirac categories. And the reason why we first considered this question was because it allows for the construction of an action of the Hecke category, so what we call the Hecke category, attached to the affine Wald group. So the affine Wald group is something that I did not properly introduce, but this is some Coxeter group that plays an important role in the representation theory of reductive groups in positive characteristic. And to this affine Wald group, one can attach something that we call the Hecke category. So this is this category has various incarnations, but the one I have in mind here is the version constructed by Elias and Williamson. And so this is an action of this Hecke category on the principal block of representations of G. So this the category rep 0G. So the category here corresponding to the case where lambda is the character 0. And so this allows for this construction of this Hecke category. And this is interesting because this allows to prove, which provides some character formulas for G modules. So this is something that that I had studied previously with Georgie Williamson, and we had some conjectures about some character formulas for G modules, and we observed that we could prove the formula if we had an action, such an action of the Hecke category, but for a long time we were not able to produce this Hecke category, this action of the Hecke category, and so this action has to do with translation functors, where it just says that there are some nice morphisms between that relate some compositions of translation functors, so this construction with Bezrukavnikov was a way to prove the existence of this action and hence to get a proof of these character formulas. And the final remark is that there are variants for singular characters of the Harish-Chandra center. So I restricted to the case lambda equals 0 in order to simplify the setting a bit, but there are versions also for singular characters. So that's what we have about the coherent side, the coherent description of these categories of Harish-Chandra bimodules. And then I can say a few words about the constructible side. So there is another geometric story for these things, and it has to do with the Langlands dual group. So for this I want to fix some other field, F, an algebraically closed field of characteristic P, which is also positive, but P different from L, because now I will consider some étale K sheaves on some schemes defined over F. And over this field I have another group, another reductive group H, so a connected reductive group over F, whose Langlands dual is the Frobenius twist of G. So the Frobenius twist of G is isomorphic to G, but if you don't want to choose extra structure, we really want H to be Langlands dual to the Frobenius twist of G. And I want to consider the affine flag variety of this group. FLH So I will not recall all the details of the construction. This is something rather standard. I take the LH is just my notation for the loop group associated with H, and IW is LH is the loop group of H, and IW is an Iwari subgroup. And when I take the quotient, I get some in scheme, which is of infinite type. So, well, this is something which is not of finite type, but over which one can still study categories of étale sheaves without any particular difficulty.
So when you take the Langlands dual, is it the other group is defined over which field?
So this H is defined over F, and G1 was defined over K.
Of different characteristic.
Yes.
And so how do you pass to, are they split, or how do you pass from?
So I work over algebraically closed fields, so everything is split. Okay, so the affine flag variety is something nice, but I have to consider some variant which is slightly more technical and a bit less standard, which is now, well, I want to consider the quotient of the loop group by instead of quotienting by the Iwari subgroup, I want to quotient by the pro-unipotent radical. Of my Iwari subgroup, and so what I get is a torsor over FL for the maximal torus, of H. So that's still an in scheme, and now I want to consider the action. Well, I still have an action of the Iwari subgroup, but I want to restrict it to the pro-unipotent parts again. And I want to consider a certain category of sheaves on this thing that I will denote by d hat Iwari-U. So I will not be very precise once again about the definition. This is Yun's completion of the Dirac category of the Iwari-U equivariant Dirac category of étale K sheaves on this thing, which are locally constant with, okay, I'll write it and then I will explain, locally constant along Iwari orbits with trivial monodromy. With unipotent monodromy. So let me explain now what I mean. So I consider étale sheaves on these in schemes equivalent with respect to the action of this. But I don't want to consider all kind of things. I restrict to the complexes which are well along the orbit of the Iwari subgroup on this in scheme. They are of the form, well, they're isomorphic to a product of an affine space and a torus, and the maximal torus of H, in fact. And I just want to obtain things such that the restriction to each orbit is just an extension of copies of the trivial local system on the orbit. And that's what I mean by unipotent monodromy. So the restriction is not necessarily constant because, well, they are non-trivial extensions of the trivial local system. But I just allow extensions of copies of the trivial local system. And so that's the category that I really want to consider. But it's for some purposes, it's not big enough. And one needs to complete it in a way. And the technical details of this construction were worked out by Zhou Weiyun, and we just take his construction, and we get a triangulated category, which contains the category that I described, but it's a bit bigger. And this is a monoidal category for a natural convolution product.
So there is no finiteness assumption. So when you say locally constant, it seems to me that since direct limit of locally constant is not exactly locally constant, you have to say it more precisely.
I take I only take local systems of finite type. I mean, I didn't say it properly, but I take constructible things. And then there is some kind of completion procedure that tells me that I am allowed to take limits in some direction, in some sense. And well, one reason why we need to do that, for instance, is that the category that I described, it's monoidal but without a unit object, and that's, well, it's usually nice to have unit objects, and this completion creates, in particular, a unit object for this product. Yes, so I can now state my second theorem. So this is still with Bezrukavnikov in the same series of papers. What we obtain is that there exists an equivalence of, again, an equivalence of monoidal triangulated categories between the giraffe category of Harish-Chandra Bimodules and this category that I just defined. Well. So I will, well, not say much about how you construct such an equivalence, but well, in the very end, this builds on the geometric Sataka equivalence and also some important construction by Getzgery, which upgrades, in a sense, the description of the center of the affine Hecke algebra by Bernstein. And while building on these tools, we were able to construct such an equivalence. But I want to say a few words about some consequences about two consequences of this equivalence. So the first one is
you are running out of time.
Okay. Yes, I'm really sorry. Yes. So I was wrong with the timing. Oh, okay. I'm sorry. So just one. So I will say just in 2 words. The first one is that by combining combining the two theorem, one gets an equivalence between coherent sheaves on the Steinberg variety and constructible, and this category of constructible sheaves, which is a counterpart for characteristic L coefficients of a previous construction of Roman Bezrukavnikov, which plays an important role in the geometric Langlands program, and so that was one of the motivations for this construction, and maybe I will skip the second consequence. Sorry again for the time, and thank you for your attention.
There are questions?
Yes, 2 questions.
Yes.
Okay. So if you consider Harish-Chandra Bimodules in characteristic 0 this time,
Yes.
we have something like an equivalent of Boolean categories instead of derived categories, or it's still derived categories? I mean,
No.
I assume it is simple, right? Simpler.
a potential counterpart for this story in characteristic 0 would involve Harish-Chandra Bimodules for quantum groups. So if you consider well, the geometry that corresponds to representations of Lie algebras in characteristic 0, it has to do with just the usual fact variety, not the affine thing. And this is controlled by the finite Wahl group and not the affine Wahl group.
I'm talking about the coherent side.
Yes. So there is no coherent picture. Yes, it's
in characteristic 0, there's no coherent picture.
For this for categories of representations of Lie algebras, no. Or, well, I mean, at least the flavor is different. I mean, there are some relations with coherent sheaves, but not equivalences of categories, I think.
Okay. And my second question is, well, I'm not an expert, but you talk about Dirac categories, but I assume you may have equivalences of infinity categories, maybe, or something like that. Or
so in what we do with Roman Bezrukavnikov, we really work at the level of triangulated categories and of triangulated categories, just of honest things. For some future developments, it seems to be required to pass to infinity categories. So this is something that I am trying to learn at the moment, but. Yes, at least for essentially all of the construction, everything we just work with honest triangulated categories.
Other questions? Yes, Michel.
So in BMR there is the bimodule that appears as a bridge, like you explained. This disappeared completely, or there is some other kind of...
No, the D-modules, they also appear in this construction. So in the proof of the first theorem, we do pass through D-modules. It's just, well, as in the BMR story, the D-modules is just a bridge. You just cross the bridge and then forget about it. It's just something that we need to relate representations of the Lie algebra with coherent sheaves, but it's still there. It's still there, and again, it plays the role of a bridge. But we don't use any particular theory of D-modules. It's just.
So in some sense, about this bridge, the second thing is related to the Cartier transform in some sense. So this isomaya algebra, it's the Cartier transform of August Wojciechowski. So usually, I guess you have a kind of Cartier. The easiest example that maybe we can think of for this equivalence is a Cartier descent, like if for the D module or module with connection.
The theorem above?
Yes, the above. No, the above. Not the. So if you have, you take a condition, but you complete. So you have a kind of nilpotence condition that if for D modules, if the peak curvature is 0, you can get a module down by going down. So do you have some description for some easy examples like this? Like something that corresponds to peak curvature 0, which descend as a module or as a bimodule?
So in the usual theory of well, I don't know much about this kind of theory of D-modules, but I think that in the usual theory of Bezrukavnikov-Mirkovic-Rumynin, there is this an example of this of this thing with peak curvature, but if I remember correctly, this corresponds to specifying some Frobenius character. So I don't know much about. Yes, I'll probably say wrong things, but the kind because of the kind of I cannot say anything meaningful in this direction.
The statement is there exists an equivalence of triangulated categories from left-hand side to right-hand side.
Yes.
So of course you had no time to give a proof. So the proof, I suppose that you define a functor.
Yes.
So and then that functor will be fully faithful and essentially surjective. Yes. So first the functor. So can you give just one moment? Can you give just a very simple baby example of an object on the left-hand side, and what the functor does to it, and the object on the right-hand side that you recover.
Well, so the baby example is just the the unit object on both sides. So the unit object in here will be UG tensored with the completion of the Harish-Chandra center, and it just corresponds to the structure sheaf of the, well, essentially the diagonal copy of G tilde in the Steinberg variety. Well, so
Can you write it?
yeah. So if you consider UG and then you tensor over the Harish-Chandra center with the completion of the Harish-Chandra center at the trivial character, it corresponds to functions on delta G tilde hat, because you have to take the, well, so we have the diagonal copy of G tilde, and you take just the in here, and you take the fiber product with this.
So both concentrated in the same degree?
Yeah, in degree 0, yes. So that's just these are the unit objects for the monoidal product, and so they have to correspond to each other, and that's what it does. Well, so this functor is relatively explicit. I mean, it passes through some category of D modules, and on one side you have a global sections functor, and on the other side you have to prove that this. So for the kind of modules that we care about, the algebra of differential operator is just endomorphisms of some vector bundles, and so the relation between coherent sheaves and D modules is just tensoring with this vector bundle. Well, so the vector bundle is not very explicit, so it's difficult to really compute with it, but that's how the functor is defined.
Maybe I have not really a question, but a comment on your question about characteristic P equal to 0. I think that the coherent thing here, it really comes from the Azumaya nature of the differential operators, which is in characteristic P. In characteristic 0, of course, it's nicer, but it's different. It's something, I mean, you cannot do the same thing at all. I mean, it's my understanding of the thing. Are there other questions or comments? Or comments on questions? Okay, so before I will invite Michel to come say a few words, but first we thank the speakers again.